Hi guys, it's Kate. This video is about inverse trigonometric functions and some of the nuances that crop up when you start to employ them, especially in composition with trig functions. Let's take a look at these two functions, f and g. F is cosine of arc cosine of x, and g is arc cosine of cosine of x. And usually after first learning about inverse trigonometric functions, there's a tendency to look at both of these and think, you know what would be great? Is if we could just take a look at these and say, you know what? These two functions undo each other. So all we'd have to do is be like, arc cosine and cosine cancel each other in both of these cases. And the truth of the matter is that both f and g are just equal to x. This is wrong. Don't do it. Don't let that be you. Don't fall into that trap. In this particular problem, it's really more of an exploration of both of these functions, what makes them different, what they have in common, and the answer to that second question, what they have in common, is actually not very much. So no, this is not the case. Don't let yourself be that person. And in fact, I even say when you're doing work with inverse trig functions, and if there's a composition where you have arc cosine and cosine next to each other, I don't even allow myself to get in the habit of crossing them out. They don't cancel. In my mind, that is not at all what they do, because arc cosine is not the inverse function of all of cosine. Arc cosine is only the inverse function of a little tiny bit of cosine, and so it matters sort of what is the value of x? What interval are you on? What order are these functions being taken into consideration? So take your time with this. Don't let that be you. Don't take the easy way out. Don't just sort of slash and burn, and take a look at what makes these functions so different. All right, so let's go back to the beginning. All right, fresh page, clean start. First question for you, what are the domains of these two functions? Because if you're looking at these two functions and thinking they're the same, well, the same functions have the same domain, and right away, you're going to start seeing that that's not the case, sort of right off the bat. Let's take a look at f. Remind yourself that when we say, what is the domain of the function? That means what are the allowable inputs? What's the set of allowable inputs for the function? And both of these functions are functions of x. So don't get caught up in the fact that this is a composition of two functions, that there's cosine and arc cosine. You want to ask yourself, what is x allowed to be equal to in order for me to get a valid output for this function? So let's take a look at f. We're over here. X is first acted on by arc cosine, and that's pretty critical, because arc cosine needs to take in a valid cosine value and spit out a value between 0 and pi, which is a distance around the unit circle, whose cosine value was that original value. So x right here, needs to be a valid cosine value, which means it needs to be between -1 and +1 inclusive of those endpoints. And then it'll compute some distance around the unit circle between 0 and pi. And can I compute a cosine value of that? Yes, cosine out here is not picky at all. So the cosine here is not putting any additional restrictions on what x could or could not be. So it's only the arc cosine piece that is really doing the restricting. And that means that x can only be equal to values between -1 and +1 inclusive of those endpoints. Now let's turn our attention to g of x. The very first thing that acts on x is cosine. So ask yourself, what does cosine do? Cosine takes a distance traveled around the unit circle and returns the x-coordinate of its location. A distance traveled around the unit circle could be any real number, right? The positive ones go in the counterclockwise direction, the negative ones go in a clockwise direction. Cosine will take in any real number. And cosine of x is going to be a cosine value. So what is inside here, right, is really going to be between, once cosine of x is computed, is between -1 and 1. Can we then take arc cosine of that? Yes, absolutely. All of the cosine values are within the domain of arc cosine. So there are no additional restrictions required on x in order for this secondary computation to take place. So x here in g could be any real number, right? It could be -infinity to +infinity. Those aren't numbers, those are concepts. But what I mean is -10 million or +10 million. It can be as large as you like. This piece, cosine, will convert it into a cosine value, which will put it nicely in the domain of arc cosine, and there will be a valid output for it. So for g, x can be any real number. The next question in our exploration is, On which interval or intervals are these functions equivalent to the identity function? So where is f of x equal to just x? Where is g of x equal to just x? Meaning, where does the function effectively just return its input? Or does it do that at all? So let's take a look at f. This is pretty interesting. Say we're on the domain from -1 to +1. These are all cosine values, right? The very first thing that happens when you compute arc cosine of a cosine value is it gives you a distance traveled around the unit circle that has that cosine value, right? So this piece is a distance traveled around the unit circle that has that cosine value, and then you compute cosine of it, and you're gonna get that cosine value. So you start with a cosine value, say something like 0, right? You compute arc cosine of 0, that'll be pi over 2. That's the distance between 0 and pi that has that cosine value. And then I compute cosine of pi over 2. I'm going to get 0 again. So this seems to do, by restricting it to the domain here from -1 to +1, you're going to receive a distance traveled around the unit circle between 0 and pi that has this cosine value that you just plugged in. And then we're going to take cosine of that distance around the unit circle. So we're going to get that cosine value back. So for all x on the interval, for all x in the domain, f of x is just going to ultimately return the input you gave it. So now the question becomes, if I look at what g does to some value for x, is it just going to return the value that I originally put into it? And already by looking at the function, I'm gravely concerned about that. What we had lucked out with in f was that arc cosine was super picky, so we weren't really dealing with a ton of values for x to begin with. But here, cosine is not picky at all. It can take on any x as an input, but then the last thing that happens before g, the function mapping, is complete, is that we take arc cosine of whatever we have from cosine of x. And arc cosine has a very limited range. Arc cosine only spits out things from 0 to pi. So, geez, well, let's see if we play it safe and we plug in something like pi over 2 for x. We know that cosine of pi over 2 is 0, and arc cosine of 0 is pi over 2. And at first, you might want to breathe a huge sigh of relief and think, oh, then g basically does the same thing as f, right? Well, my concern is, what if we picked something to set x equal to that was outside of the output for arc cosine? So arc cosine goes from 0 to pi. Let's pick something outside of that. So something like 5 pi over 2. We know that cosine of 5 pi over 2 is 0, and arc cosine of 0 is pi over 2 again. So when we set x equal to pi over 2, we got pi over 2 back. Right? Pi over 2 is a valid output for arc cosine, the very last function in the composition of functions that make up g, the function. But when we pick something like 5 pi over 2, arc cosine is not going to return an output of 5 pi over 2 no matter what, because it only returns outputs between 0 and pi. So that definitely breaks down. We really need x to be somewhere between 0 and pi in order for the function g to return our x to us after cosine has taken effect and after arc cosine has taken effect, because that's the last output, right? That's the range for arc cosine. So this is only, g of x is only going to be equal to x. It's only going to give you what you plug into it if your input is between 0 and pi to begin with. Now the next question in our investigation is, are these two functions periodic? Well, remember that periodic means that the function repeats forever. If f only has a domain from -1 to +1, there's no way that it can be periodic. It needs to repeat forever, so it doesn't really repeat at all. Now we turn our attention to g. Is the function periodic? And you might be looking at, well, I'm not really sure. It's a composition of two different functions. And we realize that one of the functions that it's a composition of, right, cosine, is periodic. So that means that this function right here, cosine of x, is going to repeat every 2 pi, right? That's the period of cosine of x. And so if this piece repeats every 2 pi. That means the input to arc cosine will repeat every 2 pi, which means that in this particular case, arc cosine of x will repeat every 2 pi. So if the input inside this composition of functions is periodic, that's going to make the whole thing periodic with the period that this inside function has. So g of x is periodic with a period of 2 pi. Now we're almost ready to sketch these functions. We know that g is periodic with a period of 2 pi. We know that from 0 to pi it's equal to x. And now the last question before we make a sketch is, well, okay, if the period is 2 pi, what happens on the other half of the period? What happens if x is between pi and 2 pi? So say x is somewhere between pi and 2 pi. I've put it here in the third quadrant, and it is some distance traveled around the unit circle that's greater than pi but less than 2 pi. And I want to know, as I apply g to it, first, what is its cosine value? Well, its cosine value is going to be its x value, the x coordinate here, located on the unit circle. And let's take a look then of what arc cosine of this cosine value would be. So if I wanted to isolate the cosine value, I'm going to put a vertical line that shows its horizontal position, right? And if I were going to ask what is arc cosine of x, that would be what is the distance traveled that's between 0 and pi, so somewhere up here in the circle that has the same cosine value as x does, and it's going to be this point right here. We need to try to describe that location, knowing that this distance is x. What is this distance going to be? And it's going to be 2 pi minus x. So note that this distance all the way down here and then this distance here are the same magnitude but opposite directions. So we're going to notice that that yellow point is where you would end up if you did one whole lap and then moved x units in a clockwise direction. So that is 2 pi minus x. And that's what's going to happen whenever x is between pi and 2 pi. So say, for instance, x was down here, right? This is outside of the range for arc cosine. Its cosine value is going to be the x coordinate along this particular line. When you take arc cosine of this cosine value, you're going to get this piece right here, this location, and that's going to be, if this were x, this would be 2 pi minus x. And so what we've noticed here is that if x is between pi and 2 pi, g of x is equal to 2 pi minus x. So what's interesting about this is that we know that g of x is equal to x from 0 to pi. From pi to 2 pi, we have that g of x equals 2 pi minus x. And so now we have a whole period that we could sketch, and then we just have to repeat that for all eternity to get a complete picture of g. So if we wanted to graph both of these functions, we have the little less fussy one, f here, which only goes from -1 to +1 and is equivalent to just x. So here's what it looks like. All right, so f is not so fussy. It's just the function f of x equals x from -1 to +1 inclusive of the endpoints. G of x, a little bit more challenging. We're going to take from 0 to pi, it's the same as g of x equals x, so it looks something like this. So that's all the way to pi, and this is pi. And then 2 pi minus x from x to 2 pi, so it looks like that, right? Slope of minus x, and that is down to 2 pi. And then since we know it has a period of 2 pi, right, from that deduction, we just repeat this triangular shape forever and ever. So we go up, then we go down. That was a little crooked. I apologize. But that's 3 pi, and this is 4 pi, and we can even imagine this continuing on. That is negative pi. This is negative 2 pi, etc., 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 forever. So you can see that these two functions, you know, the temptation is to say, oh, they're exactly the same, and these two cancel out. Not only are they not exactly the same, they're really not the same from the very first questions, you know. What's their domain?
What's their range? When are they the equivalent of the identity function, meaning they're giving back the input? That's different. Are they periodic? One is, one isn't. So that's very interesting. A follow-up question to this that we've explored on the next worksheet is, what is the derivative of g of x? It's clear that the derivative for f is just 1, but it only exists on this interval. So you might be able to deduce that if this piece is the function x and this piece is the function 2 pi minus x, that the derivative oscillates between, it alternates, I should say, between -1 and +1 permanently. But you can also figure this out by applying the chain rule to arc cosine of x. So I applied the derivative of arc cosine to this, and of course it involves the chain rule, so you have to leave the inside function totally alone and then multiply it by the derivative of the inside function, and that's a little tacky. I would really have preferred myself to put some parentheses there. And it's simplified into one single fraction, which is positive sine of x over square root of 1 minus cosine squared of x. And 1 minus cosine squared of x is equal to sine squared of x, so let's rewrite that. And that expression down in the denominator is positive. So square root of sine squared of x has to be denoted as the absolute value of sine of x if we're going to simplify the denominator, which we will. So this is now our expression for the derivative of g. And so we notice that whenever sine of x is a negative value, this is going to be equal to -1. And whenever sine of x is a positive value, this is going to be equal to +1. Let's take a look at what this looks like. All right, so anywhere where sine is negative, so bottom half of the unit circle, right? So that's between pi and 2 pi, 3 pi and 4 pi, etc., etc. And whenever you're in the top half of the unit circle, that's where this will be, where sine will be positive, and this will be equal to +1. Now the question becomes, what happens when sine equals 0? Well, when the sine value is equal to 0, that means the denominator here is 0, which means the derivative is undefined. So we're going to have at the end of each of these line segments, right, multiples of pi are for the x values. When x equals a multiple of pi, that's when sine of x will be equal to 0. So we have it undefined at each of these places. So we'll put open holes there. And that's what the graph of the derivative looks like. The graph of the derivative over on f would just be 1 everywhere and then undefined at the endpoints. So that would be the graph of the derivative. But it's very interesting to look at how these two functions behave so differently despite looking quite similar. And as long as you can sort of work through and follow this, I hope that it will keep you from accidentally simplifying and crossing these out when you encounter them in any sort of computational work. It really matters what order you're taking these in, whether it is effectively the identity function or not. And there are lots of fun little nuances to think about. If you have any questions, as always, don't hesitate to ask. Bye, guys.